Quickly running through these derivatives. Take that exponent, multiply by the number in front. So 3 to 5, I'm looking at 6x to the 1. Derivative of sine of x is positive cosine of x. So because of that minus sign, this will be minus a cosine of x. Down here, e to the 5x, when I take the derivative of an exponential, I get that same whole exponential back times, chain rule says it better multiply by 5. Here, I'm going to bring that exponent down. So -2 times 7, I've got -14. Subtracting 1 from the exponent, I'm at -3. And the derivative of a constant is 0. So for completeness, I'm going to write the 0 in for us. For that last one, we could do product rule or just multiply it out first. I'm just going to choose product rule because why not? So if I do product rule here, the derivative of the first part looks like 2x. Leave the second piece alone, plus leave the first piece alone, times the derivative of the second part, which was a 1. Cool. One of the things that we are going to spend a lot of time on this quarter is doing that process backwards and finding antiderivatives. We're going to have different notations for what those antiderivatives look like. But here's one of the notations that we might encounter. And I'm going to write these vertically in a weird way. Sorry. At least for the first couple. If I had some function and I took its derivative, and I told you that the derivative that I got was 10x to the 4th plus 2x plus secant squared x. The question I'm asking is, what was the original function? So if I think about how our derivative rules worked, I'm really just having to now apply those derivative rules in reverse. So when we take a derivative of something that looks like a number times x raised to a power, we end up multiplying that power down in front and then subtracting 1 from the exponent. So if I took the derivative and the answer I got had an x to the 4th, what was the power that we started with? It had to be x to the 5th. And 5 times what would have given me 10? If I ended up with something that had an exponent of 1, then the old power had to be at 2. And 2 times what gives me 2? 1. If I took the derivative and what I ended up with was a secant squared, which trig function did I take the derivative of? I'm about to make a really dumb math joke, but I promise I'll only make it once. Do we think we got the right answer? Are you pretty confident that we got each of those pieces right? How many people think yes? We're pretty confident we got each of those pieces right. Yes. Here's my really dumb math joke. Say yes in Espanol. So don't forget to add the plus C. So that, I know, dumb math jokes. So that plus C part, when you think you're done and you're like, just say it in Spanish. Okay. That C back there is because we could have had any sort of constant tagging along on the end. And when we took the derivative of the constant, we had that invisible 0. And anytime we're doing these antiderivatives and we don't have any more information, we're going to end up with a plus C on the back. Okay, let's step it up a notch. And I won't do the notation backwards like this. So find f of x if f prime of x is equal to How about we go with, we ready for a little bit of messy? Okay, so let's do 10x cubed minus 4x squared. I'm just gonna do one more kind of straightforward-ish. Plus 7. So we're starting with the derivative. We're being asked for the function. And we're really just doing this process in reverse. So we'll do this one together and then I will give you all one to do on your own. So I'm just reversing the process. I've got a number times x raised to a power. So if I add 1 to the exponent, I would be at x to the 4th. And 4 times what would give me 10? Good news, you don't have to guess. Just leave it as a fraction. So I've added 1 to the exponent and I'm going to divide by the new exponent. Because if I reverse that process and take the derivative, the 4 would come down, cancel out with that 4, and I would get the 10x cubed we needed. So on my next piece, if I add 1 to the exponent, and then I'll just divide by the new exponent. By the way, it kind of works on a constant, but I think it's less cognitive load if you just remember that when we find the antiderivative of a constant, it's that constant times x. And then because we want all of our points, we're going to make sure to add in a constant. By the way, both this guy and this guy have a name, and they are called differential, which just means they have a derivative in them, equations, because they have an equal sign. We're going to spend a lot of time both this quarter and next quarter talking about differential equations. And it just means something with a derivative and an equal sign. By the way, we would call both of these pure time differentials, even though there's no t in there. We call them pure time differentials because the only variable in there is the variable that would sort of be in the denominator or the thing we took the derivative with respect to. We'll talk about other kinds of differential equations a little bit later, but for now, we just have pure time differentials. Okay, so find y if dy dt, just changing up the variables on us a little bit. So here's one for you to have fun with. Let's go with square root of x minus e to the x plus 1 over x squared. Now let's make that 4 over x squared. My first line of defense when I walk up to try to find an antiderivative is I'm thinking, can I make it look like a number times x to a power? Because a number times x to a power is the friendliest thing for us to deal with. So before I try to take the antiderivative, I'm just going to rewrite this to make that x to the 1/2 and 4x to the -2. Because once I have a number times x raised to a power, I know that my antiderivative says add 1 to that exponent and divide by the new exponent. That's an exponential. The derivative of e to the x is e to the x, which means the antiderivative of e to the x is also e to the x. And then I'm looking at that 4x to the -1, sorry, to the -2. So I'm going to add 1 to the exponent, which is going to give me x to the -1. And then I'm dividing by that new exponent. And I will go ahead and add my constant in. Okay, I'm really going to write this one with t's. So we're going to do this one together. But I have given us some additional information, and that additional information over there, we call an initial condition. Which in fact makes this entire thing an initial value problem, is sometimes how we categorize that type of differential equation when we've been given some additional information. Okay, so if I am looking at e to the 5t and I'm thinking, whose derivative landed me at e to the 5t? Well, I know that when we take the derivative of an exponential, we get the exponential back. So if I were just thinking about, well, what if y were e to the 5t and then I took the derivative, what would I get? But we don't have that times 5 over here. So to sort of correct for it in the same way that we do when I have a number times x raised to a power, I'm going to divide by that 5. So from this first piece, this is going to look like e to the 5t divided by 5. Because when we're finding an antiderivative, if we want to check our work, if I were to take the derivative of that, I'm supposed to get the e to the 5t back. Similarly, with that sine of 2t, if I had, whose derivative is equal to negative sine? So if I had just made the guess that cosine of 2t was the function, then when I took the derivative, I would get negative sine of 2t times 2 because of chain rule. And we're going to sort of undo that chain rule in the antiderivative way by dividing by the number instead of multiplying by it. So when I undo that chain rule, I'm going to end up with plus cosine of 2t over 2. And then I'm going to remember to add in the constant. Now, what that initial condition is telling us is here's our generic family of functions whose derivative is e to the 5t minus sine of 2t. But we're looking for the specific one and the specific constant that matches this initial condition. Now comes the algebra part. So if I need f of 0 to be equal to 4, then my y value should be 4 when I plug in 0 for t. What's e to the 0? So I would have 1/5 plus, how about cosine of 0? Also 1. So I would have 1/2 plus that constant is equal to 4. I could have made this easier on us, but I didn't today. Fractions or decimals, how do we want to work? You got it. So if I were trying to solve for c, I would either need to get a common denominator or multiply by the common denominator. I'm a multiply person myself, so I would take both sides of this equation and multiply by 10. So I would have 40. And then as I distribute the 10 in, I would have 2 plus 5 plus 10c. And kind of running out of space there, but that looks to me like 33 is equal to 10c, or c is equal to 33 over 10. And that is what I would plug in for c. I have a position function, and I don't know why, but we often use the letter S for the position function. Pretty sure it's a physics thing. But if this is my position, then our velocity function comes from taking the derivative of the position function. And my acceleration function comes from taking the derivative of the velocity function, which means it's the second derivative of our position function. That seems not very well focused. That look better? A little better? Okay. So in 17A, I might have given you a position function and asked you questions about the velocity or the acceleration. 17B is kind of all about going backwards and thinking about antiderivatives. So now we might be given an acceleration function and have to answer questions about the velocity or the position. Fun things that maybe you know from a high school physics class. Does anyone know the acceleration due to gravity on Earth? The value of it? Cool. So on Earth, acceleration due to gravity is a constant -9.8 meters per second squared. We could make our lives easy and call it 10, but I'm not going to. I'm going to go with -9.8. So if that's our acceleration function, and I happen to know that, let's see, what should we throw around today? O'Keeffe's Lip Repair All Day Moisturizing Sunscreen happens to be up here. This is what we're going to throw around today. I'm going to say that that's about 1 meter off the ground. Okay, so our object is starting 1 meter above the ground. And for no reason at all, I don't even know what this is. For no reason at all, I'm going to send this thing upward at, what do we think that was? How fast was it moving? Let's do that again because it was kind of fun. Sorry, those of you on Zoom can't see this. Okay, let's say that was shooting up at 0.5 meters per second. It didn't get very high, right? Okay, so let's say that this thing has an initial velocity of 1/2 meter per second upward. And what I really want to know is what was the height of the object 0.1 seconds after the initial time. Okay. So I'm trying to get to this position or height function. And I'm starting from the acceleration, which means I'm going to have to do the backwards thing and find some antiderivatives. So I'm starting with an acceleration function. I'm going to ditch the units just so that they're not too much in our way. So when I go to find the velocity function, I'm looking for the antiderivative of -9.8. Perfect, because it's just a constant. And now I've got to remember, I need plus c. Now, when we're talking about acceleration and velocity problems, sometimes we like to use fancy physics notation. And instead of calling that a constant, sometimes we call that the initial velocity. It's okay to use the c, and it's okay to use this v naught thing. So now I'm looking for something in the problem that's going to help us to solve for that constant. And the thing that I know is that the initial velocity was 1/2 of a meter per second. So that means that really my velocity function should look like that word initial usually means we're plugging in 0 for time. And if I plug in 0 for time, then that velocity should just equal that V0 value, or I'm going to have negative 9.8 t plus 1/2. I'm going to write, yeah, sure, I'll write 1/2. Now that I've got my velocity function, I can get a position function by taking that antiderivative. So I've got that negative 9.8 t. I need to add 1 to the exponent. So I would have negative 9.8 t squared and then divide by the new exponent. That 1/2 part, it's just a constant. So when I find the antiderivative, I'll have that constant times t. And then because I found the antiderivative, now I've got finally plus a constant. And then I look to the problem to say, hey, was there some information that's going to help me to find that constant? Or we can write it in the fancy way and say that initial position. And our initial position was 1 meter. So our overall function here would look like negative 9.8 t squared over 2 plus t over 2 plus 1. Answering the final question of what was the height when of the object, essentially when t is equal to 0.1, I would just plug in the 0.1. So s of 0.1, I'm not going to worry about this without a calculator. I'm just going to plug it in. And it's totally fine to leave our answer with it just plugged in.